approximately 33% of that with propane. The reason why we chose propane is because it's already in a gaseous form. It doesn't need an expensive method to atomize and vaporize the fuel. So we're going to go with propane, and off of that, and its burning temperature, we need our exhaust temperature to be around 1,000 to 1,300 Fahrenheit. That's what the turbocharger manufacturer calls for, so we need to bring our temperature down to that. And using those numbers and the stoichiometric ratio of propane and air, we have a fuel mass flow rate of 3.41 grams per second at max power. So with that established, we now move on to our simulations. This is the flame tube in the combustion chamber Andrew described earlier. Our initial design, you can see the primary, secondary, and tertiary holes. There's our initial simulation for velocity. We need a very clean velocity profile because otherwise if the velocity is too high, it will lift the flame off and away from where the combustion is taking place in that primary zone there on the left. And if that happens, it will potentially put the flame out. So we need to keep the flame stable and in that primary zone. And as you can see in that simulation, the velocity in that primary zone is about 12 to 15 meters per second, which is too high. We need to bring it down to about 4 or 5 meters per second. So we obviously had to make a lot of adjustments. And after about 15 hours of simulation, moving on to our next slide, we have the profile of our finalized flame tube. You can see that it's much cleaner, the velocity is much more stable, and the axial velocity, which is what we're concerned with, the velocity leaving the tube, is now within that much lower 5 meters per second velocity. So that should be a good place for us, so we can start with our design of the flame tube now.
Our fuel system is going to be utilized with a propane tank, a normal 20 gallon use for your grill, gives us about 30 minutes of run time. And the fuel system pressure is going to be 20 to 30 psi, so we had to customize a nozzle on the right hand that you see. It has 9 endpoints to spread out the fuel to lower out the velocity at the very beginning of the flame tube.
So here's just the 3D model. So it works just above everything that we just talked about, our turbocharger and combustion chamber. Just all views just to see the end cap and spark plug and the fuel nozzle, as well as the tube that allows the air from the compressor to go into and surround our flame tube inside the combustion chamber. So here's our lubrication and cooling system. Our lubrication and cooling system is primarily for the shaft and bearing around the turbocharger that allows for the compressor wheel and the turbine wheel to spin. The lubrication is using, or the oil system uses a pump that we're setting around 40 psi to pump into the turbocharger to make sure that it is keeping lubricated during the process of us running the engine. Our main priority for cooling is while it's running, but after it's running, we turn the engine off. We don't want any heat that is from the turbine to soak into the side of the compressor or damage other parts after we turn it off.
Our electrical system will consist of a 12-volt battery, which is 20 amperes current, to power our accessories, which are the cooling fan, the igniter, the oil pump, toggle switches, and the igniter button. You see the wiring on our SolidWorks drawing there. That's going to go to our on and off switch and our igniter.
So now with all the sub-assemblies explained, here's the full assembly package. Pretty much you can see all the different sub-assemblies, components of our design. This is what we plan to have built within the next 2 months of our final semester.
Our overall dimensions and weight is going to be about 3 feet in length, a little bit over 3 feet in height, by 18 inches in width. It's going to weigh around 86.5 pounds.
Here are just our overall specs of our whole system. Just going through reviewing everything that Pat and John talked about. We have our combustion chamber showing the mass flow rate. We have our heat transfer for the oil and cooling system.
So pretty much now you might all be asking yourselves, even if this project works, what would I do with it? Even though you've salvaged and saved and used a lot of junk turbos, that's great, but what are you going to do with it? So we've posed some possible applications that we came up with. Obviously, it's a gas turbine, so like a lot of industries use much bigger versions, but you could potentially use it to run a generator. That's its own project. That's not within the scope of this senior projects, but that is always a possible solution. We believe, though, that the biggest area for this would be in the hobby industry. We believe that there's a lot of people out there who would love to get their hands on a miniature gas turbine and potentially jet engine and use it for whatever applications they want. And as of right now, it's very, very expensive. But as you will see soon in our budget, we have our total cost less than $500. So it would be very feasible to attain for any enthusiast out there who want it. And then finally, we also have been doing a lot of research in this project as well, which has been a huge advantage for us.
Here's our budget, as Pat just pointed out. We're sitting at our balance of $400.72, which leaves us a buffer of just about $100. So we can add anything to it if we have time or make it even better. And our work breakdown schedule, big emphasis on our prototype build #1. We plan to have that built and testing within the first month of next semester.
So moving forward to next semester or past this presentation, we're just ordering our main components, so our turbocharger and our fuel, our flame tube. So ordering our turbocharger is a priority just to make sure that once we finalize all the measurements on the turbocharger, make sure everything's the right size, we'll be able to order the rating parts, and then once you receive those parts, we should be able to begin assembly, and then after that, hopefully start to get testing.
Finally, here's our reference sheet. And then we would also like to thank Dr. Kumari, who's been our advisor on helped us along with all of our material and research. Questions? Yes?
I'm going to slide down.
Slide.
I think you know what I'm going to ask. What's this
Oh,
based on?
With the simulation? Yeah, no, same. I mean, we used the ANSYS fluid simulation as well.
What's your rental? What? Okay. Come talk to me on it, please.
Okay.
But a real quick actual question. What's your anticipated RPMs for this, and how does it compare to just driving down the highway out in the turbocharger?
So we based our mass flow rate on the max flow rate of the specified turbocharger. So we won't exceed that max flow rate. So it will be within the bounds of the RPM. So for a standard turbo, I mean, you can expect anywhere up to 130, 140,000 RPMs.
Now, my question then is kind of, you don't redline your car the entire time
No,
you're driving.
exactly. So that's a good point. So for us, we pretty much, for all of our calculations and research, it was all at max power. So we won't ever run it at this. We just have to make sure it would operate at max. So we know it runs at everything like that.
So yeah, I've seen some YouTube videos of some redneck engineers around turbochargers, and they glow cherry red, and I've seen a few catch fire. One, please don't start burning center down, and two, don't end up in the hospital. And three, how do you intend? What's your thermal management for the housing of the turbocharger?
So essentially, so pretty much the only component that will be too hot for the material that is within is the primary zone on the left there in that first zone. And so pretty much as long as we keep the mass flow rate flowing through that flame tube, that will create a cushion on the inside and keep the flame off directly off of the metal. And then that would prevent those temperatures from fully touching that metal and will keep it.
I think I might be on this for saying something. Can you go back to one of your system diagrams real quick? I think it's in a slide. Wait, perfect. Okay, so you have this exhaust that is coming out and feeding
is the exhaust. That's the exhaust leaving. There's an intake on the other side.
Okay.
John, could you put to the? Yeah, there you go. Yep. So on in the image there on the right, that's the intake you see in the front there, where the hose is coming out of.
Oh, so it's pulling in fresh.
It's pulling in fresh air. It compresses it, into the combustion chamber. That's the left pipe
Okay,
there.
then, I'm taking a little time. Please stop me there.
Any other questions?
So for your requirements, you said it needs to function for 500 hours, and yours is running for 30 minutes. So do you have plans to up that?
This was just the basis of a normal lifespan of turbocharger.
Oh, okay.
So like before you need to replace the turbocharger.
Okay, so not like how far?
Exactly.
So I really like those. Did you create those CAD models from scratch, or you actually leverage somebody else's?
Everything but the turbocharger.
Okay.
Because the turbocharger is super intense.
Outstanding work. I just thought you can make it easy. Okay. All right. Secondly, is that where are you really planning to do the physical experimental testing?
Yes.
Or where are you going to be doing that?
I mean, so fortunately, with just
The reason I ask is I always try to stay away from you guys.
exactly. So
That's why if you're doing the wiring stuff is out.
so fortunately for this, the highest pressure it's going to see is about 20, 25 psi.
This might be a dumb question. So take it incremental. Is it possible to, before you do the combustion, do compress the air testing and see how it goes? Or I know that might be dumb, but
That is
don't
possible.
be like ambitious. Don't be like a just everything, like one try that everything works. Be incremental. Safety first. Very, use like compressed air. We really want to introduce the combustion kind of slowly and not just one.
Absolutely, yeah, thank you.
Also, as you said, do this with compressed air to start, or even just do it when you start a motor, just manually cranking the thing.
That's how we plan to start it. It's like using a leaf blower and sending it through there, and it'll operate the system at a much lower speed, and you can test the pressure.
Make sure that you have some way to shut this thing down.
Exactly.
Because I've seen ITA 11 actually have a jet engine, and you always have to put down on that red button.
Yeah, it's the same. We'll have that for sure. Safety is obviously our main concern here.
We have time for one more question? Or break? Okay, thank you guys.